This is the multi-crystal oscillator with 21 crystals in parallel from my previous video nerds114. I have it operating in this position for particular reasons. Here I'm measuring the phase noise with two different instruments at the same time. One is the PN2060, this white window, and behind it is my Linerod software together with a direct conversion receiver. Both methods give the same result. At 0.1 Hertz, that is here, I can read -88, and 0.1 Hertz -88, and it says -88.4 up here. And at 1 Hertz, that is here, I see -132. And here it is more questionable, but 132 looks quite okay. But this is more noisy. They have been running at the same time on the same signals. I have a second instance of Linerod running. Here it is measuring Allen deviation, which doesn't look particularly good. Then you can see here is when I entered the room and caused interference to the setup. And it even looks like it is a little bit more noisy here. In this window I have frequency as a function of time, and I move the scale vertically, and you can see it is rather noisy here. The red trace is the frequency difference between my reference oscillator number 2 and the multicrystal oscillator. And the green is the frequency difference between my reference number 1, which is the Wenzel oscillator I have, and my device under test. And you can see these curves are very highly correlated, which means that the problems originate in my multicrystal oscillator. I can change the scales in the Linerod phase noise measurement. Like this, I get a wider x-axis, so it is easier to see. And I can shift vertically. Well, before that I look at the amplitude noise, which is far below the phase noise. And there is something odd with my channel 1 oscillator. Why it behaves like this, I don't know. And when I look further away, above 2 Hertz, the signal to noise ratio is far from good enough. You can see that the red dots, which is the imaginary part, have the same level as the yellow. And there are also blue dots down here in the noise occasionally, which means that the correlation is negative. And I could estimate that the phase noise at 100 Hz has to be below -168. The PN2060 at 100 Hz, it has not converged, because I can see these little circles everywhere, but it indicates that it should be below -175. But that's out of specifications, so very hard to say. I now gently change the orientation of the box. Like this, so I can open it later. And of course, Mechanical vibrations creates a lot of noise. You can see now the frequency is slowly going upwards here because the temperatures inside the box is changing because it's now rotated by 90 degrees. It is not very clear that this is wider now. Last time I tried it, the difference was much bigger. But if I look at this other screen, here it is very obvious that the carrier is wider. There are these noise sidebands you can see. And I have restarted the PN2060 and I expect to see noise here below 1 Hz offset. I restart the lead rod noise measurement also, like that. These noise sidebands, the fundamental and the overtone, are very strong. You can see they are out of scale also at -70 dBc per Hertz. I can look for the amplitude modulation, and it is also strong, much stronger than before. I had a flat amplitude noise floor here before. This is new to me. I haven't seen it before because what I saw here was random noise and not characteristic frequencies like this. I see the phase modulation in PN2060 also, of course. It is a sharp peak here at -60 dBc per Hertz, about maybe 0.12 Hertz. The noise at 1 Hertz offset is not much affected. It shows -130, but far from convergency in the PN2060. When I look at Linrod at 1 Hertz, it has not converged, but it seems to be at -133. Well, if I wait long enough, it might be -132 instead. I don't know, but I will now change the orientation of the box again. I have tilted it slightly. This is how I typically would have it sitting when opening it and making modifications. And now this trace is clearly wider than before. And there was a big jump in frequency. I shift the vertical scale a bit. Air is circulating inside the box. Now it is sloping, so it is there are larger height differences to make the air circulation easier inside the box. So the frequency is drifting rapidly now. The frequency drift has stopped. It seems to have turned a little also. I go back to the original vertical scale, 0.02. And here we can easily see how it had the maximum and then turns back. Now the phase noise is much stronger close to the carrier. And you can see it here, how this has widened. And you can see here at 0.1 Hertz, I see -68. And it was about 80 before, so that is a 20 dB loss. And if I look at the PN2060, you can see it looks like this. It says -70 at 0.1 Hertz, and I said minus 68. Well, I didn't start them exactly at the same time. I will restart both of them now. I will leave this running for a while. I want to see that this noisy situation is stable, because the next step is to open the box and try to remove crystals to see if I can find if there is one of them that is particularly problematic and sensitive for the orientation, which the crystals shouldn't be, not to this extent. The crystals I use, they are industrial waste from a lab where they have been tested. And I guess one of the tests has been vibrations and another mechanical shock, and also electronic things that I don't know anything about. When I opened the oscillators, I found a couple of crystals that were completely dead. So there is seemingly at least one which is half dead. The PM2060 and Lindrad show the same thing. A lot of noise below 1 Hz offset, and there is some structure in the noise. Maybe it is better seen if I go for the spectrum. Well, it is very clear that there is a spectrum here that originates in the multicrystal oscillator, because the green and the red trace look exactly the same. It means both channels have the same signal. And that's the same as I see here. Green and red and yellow coincide all the way up to 0.6 Hz or so. Frequency versus time looks like this, and you can see the variations are the same in both channels. This is now much faster than I showed before, half a second for each pixel. I have disconnected one column with 7 crystals, and what you see now is an oscillator with 14 crystals in parallel. And here is frequency versus time, and you can see a periodicity from here to here to here, and then it is more chaotic. The phase noise near the carrier is very high, and I can see also the spectrum. There is a lot of noise. And of course, if I look at the PM2060, I see the same picture. So the problem was not caused by those 7 crystals that I have disconnected. I have reconnected those 7 crystals and disconnected another column, so there is still 14 crystals running now. And the difference is very small. Up here it looks more or less the same. I haven't run it for a long time yet, but it seems that there will be no significant difference. The frequency versus time looks very much the same also, as expected. I will leave this running for a while to look a little bit closer at it. The frequency versus time variations look a bit different. A shorter time constant, but a similar amplitude. And I don't know what to draw conclusions from that. If I look at the spectrum, this looks fairly similar to what I had before, with another group of 7 crystals not present. At 1 Hz, minus 129. And here, 1 Hz, minus 129. But strong noise closer to the carrier. Now I have removed the last group of 3 crystals and running the 14 crystals that were previously removed, 7 at a time. And the result looks very much the same when I look here at the baseband spectrum. I will wait some time to compare the PN2060 and this Linrad noise with what I had before. Frequency versus time looks very similar. I look at the phase noise. It also looks quite the same. And with Linrad, of course, I have the same. And here also. The conclusion: the problem cannot be caused by a single crystal. Having many of them behaving like this seems very unlikely. So the conclusion is the problem is not caused by the crystals. Something else is sensitive to the orientation of the box. I have connected all the 21 crystals again and placed the oscillator in this position that was more favorable. The noise is also lower now. There is some extra noise here, but not as much as before. And here is when I entered the room this time. I changed the temperature by air moving when I come in here. So maybe the problem I see is of thermal nature. I have placed this fan about 2 meters away, and it's not rotating very fast. Here is ordinary toilet paper. And when I'm away here, you can see there is some wind blowing, but not very fast. The effect on the frequency is dramatic. As you can see here, I reduced the scale by a factor of 10. Means 0.2. And you can see how it starts to grow, and it seems to be an exponential growth. So it will take some time before there is a constant temperature situation. You can see here, it is not only that the thing is drifting, it is also noisy. I changed the vertical scale by another factor of 10. I make it 2 here. And it seems to be a linear drift now, but strong. I make the horizontal scale slower to see this better. 2 seconds, that's a factor of 10. No, 5 seconds. I can see that the trace flattens out. I can change the scale again. Maybe 0.5 is suitable. And you can see it has gone from minus 50 to plus about 50 millihertz. That is 0.1 hertz is the frequency change. And when I look here, I see this signal is 0.1 hertz. 0.1 hertz per division shifted away. I have to move it into the filter to get the phase and amplitude detection back. You see the red numbers means data is invalid at the moment. So I start from scratch again here. And then the PN2060, I start that. It is not so sensitive for frequency drift because it uses another method for determining the phase. The vertical scale for the frequency versus time is now 0.2. That is 10 times less sensitive than I used to have before. And these undulations are of the same size, roughly, as they were with the other scale. So the stability was very poor here. Maybe it becomes better if I wait more. But looking here, I see there is a lot of noise. And I can check. Here I have not got any data yet, but I have the PN2060, and it shows very high noise at 1 Hertz offset, minus 110, and it has converged. So applying a modest air stream onto the box is really damaging. And here is now the phase noise, just one transform. But since I had here an asymmetric spectrum, you can see that it is stronger here than here. That implicates there should be an amplitude noise present also. So I look for the amplitude noise, and it is much stronger than normal. It is almost as strong as the phase noise. Phase noise, amplitude noise, they have the same shape, but they are not very strongly correlated. But at higher offsets, at 1 Hertz, they are very strongly correlated, and they are in phase because it is the white trace. That is the real part of the correlation. Or in phase, or maybe completely out of phase, but the phase angle is plus or minus, it is 0 or maybe 180 degrees. And that depends on how we define the sign of the phase. And here, very noisy. So this was interesting and not easy to understand. It is interesting to see that the noise seems to decrease with time as the unit comes into equilibrium with this new situation. I will leave it running for a while. The noise at 1 Hertz offset is very strong now. It's about 20 decibel above what has been normal for this unit. And I see the same in Linrad, 1 Hertz here. And this line, minus 110. So I don't understand it, but it's interesting. Now I go the other way around and decrease air circulation around the box. I have not changed the position of the box. Now, when the temperature is rising and the frequency is going down here, I can see the noise increases also. It seems that a change of temperature causes noise. Well, this is interesting. While the frequency goes down here, and then it drops rapidly, and then it continues here and drops rapidly again. That seems to correlate to this noise burst and this longer noise burst, here and here. And then it was fairly quiet, and now it is more noisy again. So I don't know. I will wait for quite some time to see if it stabilizes or if it continues to behave badly. The phase noise is of course very high. It's a nice straight line, but it starts at 10 Hertz at minus 144 and 103 at 1 Hertz. Not good at all. This seems to have done something very good. You can see here the channel 2 oscillator is far more unstable than the channel 1, which is the Wenzel oscillator. I have been away for a while and I had collected data from before it had stabilized, so I don't have any good phase noise spectrum yet. I have only a couple of data points. This has been running for many hours now, and after several hours I started measurement, and that measurement has been going on for quite some time now. The phase noise is very different from before. There is clear noise in this region, a noise hump, and at 1 Hertz it is about minus 128. So it's not so good as it was before. If I look in Linrad, it looks the same. At 0.1 Hertz, I cannot even read it properly. It comes out negative here, and the imaginary part is very close. But at 0.1 Hertz, I would guess here, that's 96, minus 96. And that is in agreement with what I see from the PN 2060. And the result at 1 Hertz here, it's not as good as before, but it's not bad. It is minus 128. And of course in agreement with what I see here. Frequency versus time. This is the 0.02 scale setting with 5 seconds per pixel. And you can see the difference between my reference number 1, which is the Wenzel oscillator, the green line, which is fairly flat, and my other oscillator, which is more noisy. And that is very clear from the Allen graph also. You can see the red points are high above the green ones. The yellow line is the correlation between these two curves, and it goes far below both of them at times below 10 seconds. So it is obvious I have a problem with temperature. It seems something inside the box is chaotic when it changes size due to a temperature change. Means it doesn't change size continuously. It makes some small jumps in size. And size means capacitance if it is some sensitive part. I will put a light source inside the box and shine light on various things to heat them a little to see if I can find where the problem is. I make an aluminium tube by placing this aluminium around the drill. The diameter chosen for this tube to fit with some pressure on this red light-emitting diode. So now I squeeze it on like this. I paint the aluminium black because I want the aluminium to take care of heat from the light-emitting diode, and also to screen the light so it only comes in the forward direction. And the black color is to radiate heat from the aluminium to help keeping the temperature low on the diode. I will start by shining light on this transformer. Here it is sitting directly on the crystals, and it is for the cancellation of signals in the stop band. I first waited about 1 hour and then started this measurement, and you can see phase noise looks fine now. It has not converged properly yet, but it shows about minus 130. And frequency versus time looks nice, and the noise here looks nice. So now I switch on that light emitting diode. Here is a transient when I pull the switch, maybe vibrations on the table. And here you can see how the frequency goes down because something is becoming warmer. Presumably that transformer, and also the air circulating around the lead. But I don't see any extra noise. And measurements take a long time. I mean phase noise measurements. So restarting and hoping to see something is not meaningful. But I can look here. This is much higher resolution waterfall. And if I see a similarity between the red and the green curve, it means there is something that is common to the two channels. But I see nothing. Well, it's clear that frequency change caused by the lamp of the order of 10 millihertz has not increased the noise at all. I remove this textile and change the orientation of the box to this position, which was bad before. Now the frequency has changed by 40 millihertz, 4 times more, and in a slightly shorter time. And I can see maybe a little bit more noise here. Hard to say. But if I look here, I can clearly see that the red and green traces are similar. Means there is noise now from the box. And if I wait for a while, I can probably see this is wider. And if I start here, I will probably see the noise level is higher again. It's quite clear here that we have these noise structures that are the same on both sides. Although there are differences also clearly visible. And I can see the white range is now wider. It seems I need more power. Like this. We will see if this heats the transformer significantly more. Now the frequency is stable enough, I think, and the phase noise is low. It's about 130 at 1 Hz. The reason I saw a not so good result at 1 Hz previously is that I forgot to restore the proper coupling after having used only 14 crystals a couple of times. Here I switched on the light, and you can see here also. And now I see phase noise, and this is spontaneous. I have not made vibrations or so. So it comes from what happens when the temperature rises. And it's not so bad. I started measurement here at the same time as I switched on the light, or maybe 1 second after. I found this sub-miniature lamp, 5 volts, 60 milliamps, and I placed it at the center of the toroid. This should make a significant difference. Here I switched on the lamp and it flattens out now. I cannot see anything on the PN2060, but I have not reached closer than 1 Hertz from the carrier. If I look at the Linrad, which has not been running very long, I can see there is a lot of noise at 0.1 Hertz, because the curves are the same, the green and the red. And I can also see, although it is only 3 correlation averages, that it looks very high. At 0.1 Hertz it is about -70. So I switch off the lamp to see the temperature go in the other direction. The speed of the cooling process a little bit slower, but still significant. Now the first correlation between the 2 spectra arrived, and I see the typical noise here that I have problem with, and I see it very clearly in Linrad, which runs a bit faster. I have removed the stop band transformer. It is not needed when the unit is an oscillator. I need it only when it runs as a selective amplifier, when the signal I feed into it has a lot of noise in the stop band, so I cannot trust what I see at the output on the stop band. So now there is no transformer with suspicious glue on it. I have been running the unit overnight in its optimum orientation and with the textile on it, and the performance I see is very good. At 1 Hertz, -134 in the table reading out the cursor. And looking here, well, maybe more like 133. I can check what Linrad is saying. It is here, 133. At 0.1 Hertz, I see -100 in the PN2060, but I can see it has not converged because there are circles on the data points. And in Linrad, I can see even worse, it has not converged. The real part is actually negative below 0.11 Hertz or so, but the imaginary part is stronger than the negative real part. So below 0.2 Hertz, the result from Linrad isn't really reliable. And I think maybe this is because of the noise in the mixers, causing a worse signal-to-noise ratio as compared to the PN2060. I don't know. I haven't seen this before, and I don't want to wait anymore. Frequency versus time looks like this. I can magnify the y-axis by a factor of 10. 0.002, and it is questionable whether there is much correlation. Well, you can see here two peaks, but often there is not any correlation. I have placed the box like this, not exactly horizontal, leaning just a little. This is a bad position for it. Here is frequency versus time. There are chaotic oscillations with low frequency, and the phase noise looks like this. I have set a smaller transform size to capture the 0.1 to 1 Hertz region relatively quickly. I placed the textile, the handkerchief, on top of the box, and that didn't make any significant difference. And phase noise looks similar. Then I stuffed the box with cotton wool, and that made a big difference. Now phase noise looks like this. I have reverted to the normal transform size of 2048. And this looks perfectly okay. And versus time, frequency versus time, is very much better. So the problem is turbulent circulations of air inside the box. I'm not so sure there was any problem with the glue on the transformer for stop band attenuation. The big problem is how air is circulating due to local heat spots inside the box, which is fairly big, so there is room for the air to make chaotic oscillations. This is what made the situation much better. Cotton filling the box. Heat is generated by the emitter resistors. I will try to arrange something to cool them better. I have glued a sheet of mica to the source resistors to get a good contact from the resistors to that sheet of mica. And then I have 2 wires, 3 square millimeters each, to the laminate up to that mica sheet, and glued from the other side, glued from both sides with epoxy resin. I have moved the 4 560 ohm resistors in the bias voltage for each amplifier stage to place them very close to the laminate, and then a small quantity of epoxy to make them in good thermal contact. They develop about 300 milliwatts each, so they may cause some circulation of air around them. But now they will heat the box walls that will spread the thermal energy around better, I think. For some reason, performance at 1 Hertz offset has been destroyed. I don't know why. I will try to change the position of the box. I've placed the oscillator sideways, which was optimum before, and also this textile on top of it. It seems this has solved the problems. I don't know what this could be, maybe minus 132. When I look at Linrad, it looks like minus 131, but statistics is not very good yet. And frequency versus time looks quite good. And as usual, when I enter the room, I change temperatures. But Allan deviation, I don't know if it is really good, but this is what I see, and to some extent the Wenzel oscillator contributes. Measurement has been running for a long time with this box. Now I put these 2 pieces of black tape on the box. That is in the order to be able to measure the temperature. The black tape has caused the temperature to drop a little with an associated frequency change of 8 millihertz. The highest temperature I can find is 44.6 degrees with this infrared radiation thermometer. I placed black tape on the entire top surface, and this caused a significantly larger temperature change up until this point, where there suddenly was a jump in the frequency. So it has gone from minus 33 to here 33 hertz, 3 times more than I got from that single tape. But then there was this jump of about 20 millihertz. When I look at the spectrum, I see this is what I had before, and this is with the single tape. I don't see a difference. Then it took some time to put all that black tape in place, and now it looks much better. I will collect data and compare spectra. The highest temperature now is 42.6 degrees, not a big difference. But frequency versus time has changed. It is less noisy. Here you can see when I was measuring temperature, I made disturbances to the box. This has been running now for 1 hour and 10 minutes with a black tape on top of the box. And here is what it looked like before I put that tape in place, particularly close to the carrier. There is a big difference. Here it has not converged yet, but this is probably going to be better than the old, which is here. But there are circles in this that hasn't converged, and the new one there are even more circles. So how cooling is obtained on the box is important. I have placed 5 millimeters of aluminium on top of the box and put black tape on top of it to ensure a good emissivity of infrared radiation. I can look at the temperature. You can see 36 degrees. It's the same, almost. Oh, I have to point to the black tape. Otherwise, I see the reflection on copper, which doesn't emit well. And to attach the thick aluminium to the box, I have used this as glue, because this is not something I want permanent. And the 5 millimeter thick is not flat. There is a 1 millimeter gap here, which is filled with this grease to give a good heat conduction. The result is interesting. It seems like minus 131 at 1 Hertz and minus 95 at 0.1 Hertz. So this is quite good, but the box is still filled with cotton, although this time the cotton filling did not work very well. I have an image here. This is what it looked like. I showed it recently. This is the same. So this improvement comes from the 5 millimeter aluminium. And for the value at 1 Hertz, I can look here on the Linrad. Let's see, where is the mouse? Yes, here. So this is 1 Hertz offset, and the level is here, and that is minus 131. So the two methods of measuring give the same result if I just wait long enough to get good statistics. I will remove the cotton from the inside to see if just spreading out the heat over the entire top was enough, or if the combination has done the trick. Air circulation is driven by temperature differences, and almost all the heat generated in the box is to the top laminate. Transistors are glued to it. Those resistors that dissipate significant amount of power are also connected to the top of the box. And now this aluminium makes the temperature the same over the entire top. And maybe this would be enough also when I take out the cotton from the box. If temperature differences are small enough, air will circulate inside the box with laminar flow. But if temperature differences come over some certain point, the circulation will be turbulent. It could even be oscillatory, as we have seen earlier in this video. So I will see what happens when the cotton is no longer inside. The problem with chaotic air circulation inside the box is solved. Just make the temperature even on the top of the box. I will find a permanent solution to that later on, but there are some other problems that I want to look at. I see minus 131 dBc per hertz here at 1 hertz offset. That is a little bit more than I had before. More noise, that is, I could see minus 133. Now this is statistically fairly certain, and I can see there is a noise hump here. So I have had something which has a maximum likelihood at about 2 hertz. And I cannot see 2 hertz in lean rod, but I can see 1 hertz, which is here and this position. And it says minus 131 also, of course. At 0.1 hertz, minus 97. That is very good, I think. And here I can see minus 97. And at 0.07, I see 89. 9, 8, 7. Well, 89 is up here. But there are circles everywhere here. So this result is not reliable yet. And here is frequency versus time. It is hard to see much correlation between red and green, except here at the end when I entered the room, because I moved the air around the box and changed the temperature just by coming here. But the green trace, that is the Wenzel oscillator, and mixed with my device under test. And it's clear I need a better oscillator for channel 2 that will make convergences faster when I do these measurements. This is the power supply for the Wenzel oscillator. I change it by 1 step, that is 10 millivolts, like that. The Wenzel oscillator is connected through a 5 ohm resistor and a very big capacitor. I don't remember exactly, but something like 1 farad. You can see now the frequency has changed dramatically. The green trace is now coming out of scale, so I change the scale by a factor of 10 to 0.1 instead of 0.01. And then you can see an odd thing. The frequency changes by almost 2 divisions. That is almost 4 millihertz. And then it changes back again. So what I see is it changes by 3 millihertz, and then it goes back with a small overshoot, and then it returns to a stable operation again. I'm pretty sure this is caused by the thermostat oven. I think the thermostat is a thermistor that is compared to a reference voltage. And when there is a difference, it will adjust the current through a heating resistor. When I increase the supply voltage by 10 millivolts, that is not a lot, then the current in the first moment is not changed, because the difference between the reference voltage and the thermostat voltage doesn't change. So the current is the same and the voltage is higher. But soon the temperature is rising and there is an imbalance, and the thermostat will change resistance, and that will lower the current until it becomes almost normal. Then there is an overshoot, because it is a servo system that is normally a little bit of overshoot to make them faster. And then after this time, and that is about 300 seconds, it is back to normal again. And maybe it goes up and down and up, but this I cannot say because my reference is not stable enough for me to say that. But one thing you can see, the red curve is not affected. That means my reference oscillator number 2, well, it may be affected because it has gone down a little bit, as you can see here, but that is maybe 0.25 millihertz or so. The red channel 2 oscillator is phase locked to the frequency of the vent cell, but the time constant is very long. So even this excursion to an inappropriate frequency over 100 seconds, that is a far too short change in frequency to affect the frequency of channel 2 through the phase locking. I have removed the thick aluminium, and you can see that the grease I used for thermal contact has been efficient. The 1 millimeter wide gap between the two has been filled with this. I will just remove this. Well, I don't know, it's probably some oil essentially, and fats. My favorite cleaning agent is isopropylic alcohol. I have used it to remove all the grease from the box, but I have not changed it in any way and not moved it. It is solidly screwed into this, I don't know what it's called, but it's in fixed position. So the only difference is that the cooling on the top surface is removed. The frequency instabilities have come back, and that is clearly seen in the phase noise at 0.1 Hz. It's degraded by about 10 decibels now. So it must be chaotic air movement inside the box. I think I have lost 2 decibels from minus 133 to minus 131. This could be because I removed the stop band transformer. So I look at the phase, I put the marker where the phase is 0, and then I look at the transmission, and you see it is not on the peak. There is a small error in the frequency. Maybe because I removed the transformer. I will put back the transformer and also put an adjustment for the phase. The stop band transformer is back. The curve is now symmetric, which it was not without it, and the frequency has changed slightly. And I can look at the phase, and now the phase function is the same, but it coincides 0 phase with the peak of the amplitude. I have placed the box in the optimum position that I learned before and placed the textile on top. And now I'm measuring phase noise. And fine, it is not good at all. Minus 121 at 1 Hertz. I have added 6 millimeters of copper on top of the box. 4 layers of 1 millimeter and the final layer of 2 millimeters. And then I have added cooling flanges from 6 millimeter aluminium. First I added this one, and then I added the outer one, this one. And the last step had a profound effect. Here is frequency versus time. And here is when I glued the outer cooling flange. And this looks far more unstable than this. And the time scale is 1500 seconds per division. So the instabilities are very slow. About half an hour. But this is better. Whether this is real or some coincidence, I don't know. I will continue to put one more cooling flange on the box. The unit has been running for 11 hours now. What I see here is frequency versus time. And I cannot say for sure whether this is the Wenzel oscillator or whether it is my box, or maybe a combination of both. The avant deviation is 10 to minus 11 at 1000 seconds. And 1000 seconds is maybe long enough for the phase locking to make both my oscillators follow the same frequency. And much longer times they are identical. But at short times, below 10 seconds, the oscillators are completely different. And I can see the correlated noise is much lower than what I have from one or the other oscillator. And that is, of course, seen very clearly in the phase noise graph of Linrad. So, the bad performance I have seen in this oscillator before was temperature-driven air turbulence inside the box. Having a big box, like the one I am using, creates problems. The temperature has to be even inside it. This was unknown, and I have probably had the same problem earlier in other oscillator designs. The phase noise, as I can see it in Linrad, at 1 Hertz, it is about here. That is minus 131 dBc per Hertz. At 0.1 Hertz, it is still noisy. You can see the imaginary part is very close to the yellow trace, but I can extrapolate and guess that it is minus 98. And I can see that my oscillators, the Wenzel, is far more noisy than my oscillator at 0.1 Hertz. And my reference oscillator in channel 2 is even worse. The PN2060 gives here minus 130.9 at 1 Hertz offset, according to the table here. And the marker looks well placed on the curve. And the credibility is good. I can see the imaginary part 10 decibels below here. So at 1 Hertz offset, the PN2060 is better than my Linrad. On the other hand, at 0.1 Hertz, it has not converged yet. There are circles here and here, and it looks like minus 98 or so. I have a problem that the noise at 1 Hertz has been minus 133 before. So there is a small loss, and I don't know why. I will try to find out later. And the result I presented now comes from the box in this situation. I have no paint on it. I think it's better to make it black, but I've not tried that yet. But cooling is now better. The temperature across the entire top of the box is very near constant. I have started the fan again about 2 meters from the box. As a result, the temperature on the top has gone down from about 34 to about 27. And I look back here, 27. But on this side here, the temperature now is only 23.8. And I didn't measure it before, but I think it was nearly the same as the top from how it feels sensing it. And the same here, of course, on the side, 25 degrees. So there are big differences now between the top and the sides of the box. The frequency has drifted significantly. I have changed the vertical scale by a factor of 100. And the deviation you see here is bigger than the normal variations I had over those 11 hours. It means the temperature in the room should be constant within 0.05 degrees or better. And maybe that is not actually obtained with my heating system, so part of the variation we saw may have been temperature variations in the room. This is highly unexpected. The noise at 1 Hz offset has decreased. The PN2060 says minus 132, and it looks like a good representativity for the noisy curve here. But on the other hand, at 0.1 Hz, the noise has increased. It is now only, I would say, minus 93. It was 98 before I put the fan on. In Linrad, when I look at 1 Hz, that's this line, I would arrive here, and that is minus 132. And at 0.1 Hz, minus 93. So I see the same things here. And frequency versus time looks fairly ugly as compared to what I saw before I put the fan on. Maybe the reduction here is because of the slightly lower temperature in the box, in the transistors, while the increased noise here is because of the temperature differences between the top of the box and the sides of the box. I will paint the top of the box black and remove the fan to see what happens. The black paint has made the color go down from 34 to 32 degrees. But at the side here, temperature is 28 only, or 25. 29, well, 30. This has been running for 7 hours now, and it looks like it has improved a little. According to Linrad, I see at 1 Hz here, about this level, that is minus 132. But signal to noise ratio is not good. You can see how noisy this track is. At 0.1 Hz, Linrad says minus 100 if I try to smooth this curve. So this is an improvement, and it's unexpected considering the temperature differences. The temperature here was 34 degrees before I painted. Now it is 32.6 or 32.2. Well, it varies from time to time, a little bit more than I'm used to. Well, if I shine on the unpainted metal, I get reflections of cool temperature in the room. I can measure more like this. 32. So it's a little more than 1 degree temperature lower on the lid. Back here it was about 33.5. And now it is 32.6 or 32.8. So just a little less than 1 degree is the temperature change. The temperature here is 29 degrees, just 2 degrees below what is on the top. But there is a temperature difference. And here, at the side of the box, 28.4. So 2 degrees or 3 degrees between the sides and the top of the box. I will put some isolation on the box sides to make this temperature difference even smaller. With plastic foam on the sides of the box, the temperature on the sides should be very similar to the temperature on the top. And that should reduce air circulation within the box, while the temperature of the top should increase slightly. And indeed, it is now, well, 33 degrees sometimes. It depends a little bit where I hold, but 33.5. It has increased by 1.5 degree. And the frequency has changed by about 15 or 14 millihertz. That's not a lot, but that's for the increased temperature by 1 degree approximately. Different things inside the box have different time constants and affect the frequency in different directions. As you can see here, it is going back closer to the original frequency, and the time it takes seems to be very long. Thousands of seconds. 1,500 seconds per division. It seems stable now after perhaps 2,000 seconds or so. This is not at all what I had expected. At 1 Hz offset, I can clearly see that the noise floor has increased. Now about minus 129. And at 0.1 it is not as bad, but I think it has increased a little also. And you can see clearly the reported noise values are well above the imaginary part here. This could be because of an interference event, or it could be because of an extreme temperature sensitivity. When I look at the lean rod phase noise screen, at 1 Hz I see this from here. 131. So it's not quite as bad. This could be because Linrod has an algorithm that detects interference pulses and excludes some sequence of data when such things happen. But that is far from perfect, but it's an indication that there probably has been some interference pulses. I can think the reason is that I have glued the foam plastic by use of double sticky tape, and maybe there are some small movements that it changes because the plastic doesn't want to sit exactly as I pressed it. The foam plastic had come loose. There was a 5mm air gap between the box and the foam on this side. Now I hope this will be stable. The change cooling has a profound effect on the frequency. You can see the signal goes here and out of scale. I have compressed the frequency scale by a factor of 10, and I see that the frequency change is about 4 millihertz. I will wait for this to stabilize before I start measurement. Well, the problem has disappeared. When I look at this, I try to avoid the statistical things, because at 1 hertz there is a peak, and I don't think that is a real phenomenon, it's just statistics. And you can see also that the imaginary part seems to be 15 decibels below, and only in a very narrow range. So I don't believe this. It looks like minus 131 at 1 hertz, and at 0.1 hertz maybe 98. If I look in Lienrad, at 1 hertz it's minus 131. At 0.1 hertz it says minus 99. Actually minus 100, but that is statistics, I think. So this is fine, but the very long time constant when switching the unit on is inconvenient, so I will not use this. I found that the source follower at the input is slightly saturated. The voltage on the drain here was clipped on the top side. To cure that, I put 1 kilo ohm from here to ground to lower the voltage on source and drain. And that reduced the power by about 2 decibels, and then there was no clipping anymore on the input stage. The effect of this was not what I expected. The noise has increased at 1 hertz offset. Now it's about 126. And here a little bit uncertain because I have not run this for very long. I will change back, hopefully get back the old result. Something has gone wrong with my box now. I just opened it and cut the wire to this resistor, and now the box is unstable. And I can see it here clearly, and of course at the sideband noise, which is now minus 125 or something like that. Maybe because the frequency is drifting and something is changing size, and when something is changing size due to the temperature, there could accumulate strain in something, and then that strain is released, and that would give an interference pulse like that. And this result is high above what it normally would be at 18 averages. I will not study this in this video. I will stop here. The important lesson learned this time is that turbulent air circulation is a problem when building oscillators in big boxes like I have been doing in recent time. Probably the high noise at 0.1 hertz offset in my channel 2 reference oscillator is caused by that problem. So I will try to make my channel 2 oscillator better before continuing investigations on this one. Addendum. After about half an hour, I can see something is much better. That's because I have cleaned the first suspect, the BNC connector at the output. And I don't want to wait 8 hours to see that it is perfectly okay, because now I want to do something to the channel 2 oscillator.